All right, if I remember correctly, right at the end of class is when I realized why we were handing out different port numbers to our different clients for testing on the same machine. Does that sound accurate?
Yeah.
All right. So current, what do I use? Do I use the blue or the purple? Ha ha. All right, so what was this saying? Oh, so right now the idea is we're testing all these in our terminal. We have our server that's running here. There's our tracker. All the clients check in with the tracker. They get a notification they've updated the client IP list. So these guys have the a thread for that guy has come up. So now what we want to do is we want to broadcast that. Let's see. So let's see. This guy got his own IP back. That was up there. We're not getting anything right now. That must have been when I was right at the end. So the idea is when this first guy connects, he's just going to get the current list of IP addresses, current list of clients. That's what the tracker gives you. When this guy connects, he's going to add himself to the list and he's going to get a dump of it. So let's go get that working. But then what we're going to need to do is every single time a client connects, this wouldn't be something we would have to do if we were guaranteed that all our clients were running on different computers. But since we're testing it all from a single computer, what we're going to do is we're going to have the tracker assign a port number to each client. Okay, client 1, your port 3000, client 2, your 3001, so on and so forth. So they all know what to bring their server up on for the peer-to-peer network. So let's see what our tracker currently does. Our tracker gets a new incoming connection. We tell it to start. It comes to our tracker thread. Tracker thread does a little bit of communication. It reads in the IP address. It then updates that IP address. So remember, we wrote this guy as a synchronized client to our synchronized method to protect our client IPs. We then asked for some connected clients. And we are writing the connected clients out right now, even though that's not what I saw back there. Let me compile one more time. So we're writing out client IP connected. That's going to be in our client driver. Oh, we're not actually writing it out. There's our list of connected clients. Then we're going to have this broadcast all the other ones. That's where we left off. Okay, so that guy gets the IP address that he sent in. This guy is going to then get a dump of 2 IPs. There's the 2 IPs. This guy will get 3 IPs. There's the 3 IPs. And again, those are all the same IPs that we're storing. So what we need to do now is we need to update when we capture an IP from a client coming in. We need to go ahead and have the tracker assign them a port. So we can have our clients uniquely do this. So I think I have a client. Didn't I have a client core? Oh, I want a client core. I want tracker. Here's my tracker threads. This guy uses normal core. All right, so for our normal core, what's up? For our normal core, we'll go ahead and say current client port, and this is a int. We'll start this guy off at, let's just do 3000. This is my tracker run on. Tracker runs on 6881. So we'll have our starting client port at 3000. And then what we'll do is we'll just give ourselves a function. And we'll synchronize this. Public static synchronize it, get next client port. And this guy will return core dot current client port plus plus. Remember, when the plus plus comes after it, it'll return the current value of current client port and then increment it. So this will return 3000 the first time, but then set it to 3001, return 3001 the second time, and set it to 3002. Good. I don't think so. Those are all just modifiers. Yeah. I do think the security needs to be the far left one, because I'm pretty sure. Maybe not. I would think it'd yell at me in here. Well, let's leave it like that. We'll see what happens in a second. All right, this is, oh, that's the client. I want my tracker thread. All right, so my tracker thread, this is the guy that receives the new client IP, and then he adds that new client IP to our collection of IPs. But what we want to do here, since we're reading this guy as a string, we want to go ahead and assign him a IP address, or I'm sorry, a port number as well. So we're going to say string new client IP plus port. So this will be new client IP concatenated with, let's just put it maybe a colon, concatenated with core dot get next client port. So it'll give us a number. So we're going to effectively store an IP address, colon, port number. All right. And then that'll be the guy we actually store in our connected clients thing. We don't need to change anything there. So let me go ahead and run this one more time, and we'll see the change that made. Oh, I'm not. Well, I should be. I'm building the string the same way. Maybe I should write the new string I just built to the core. Might be helpful. Now it's going to give me my assigned ports. So this guy got assigned port 3000. When the next dude connects, he's going to see that, oh, he was assigned port 3001. Next dude connects, he got 3002, so on and so forth. And so now each client knows what port they should start listening on. Okay, because now they're part of this peer-to-peer network, and we want the clients to all connect to each other. So that means every one of our clients, once they get that port number, and it is going to be interesting. For us to tell these guys apart since we're getting the identical IP addresses. Because he doesn't want to open up a connection to himself, is the punchline. And right now, each of our 3 connected clients really don't have a way of picking themselves out of a lineup here since the IP addresses are all the same. So what we could do, let's do this. Well, let me ask you, what do you think? I have an idea in mind. What do you think would be a good way for our client to uniquely identify themselves in our model here, where all 3 clients are running? They're all going to have the same IP address. What might be a good way for our client to uniquely advertise itself to the server so they can identify themselves out of a group? And I'll bring up the driver, right? Probably somewhere in here is where you maybe can do it. Go ahead. Okay, and what might that look like? How can we make sure each client has a unique ID? Okay. Do we have any way of getting a guaranteed unique ID, leveraging something that's already here? It's actually going to be an operating system type thing. Go ahead. Could use the process ID. We'd have to look at how Java can get the process ID of something, but that would work. Operating systems handing out a unique process ID. Anything else? Go ahead. Well, yes, but the guy would then need to, he's going to know what port number he's going to be listening on. So I suppose he could go through and say, okay, well, I'm only going to uniquely identify myself based on whatever the port number is. Later on, port numbers probably wouldn't be a thing since they'd all be listening on the same one. In this case, that would work. In this case, that would work. But let's come up with a unique way of a client advertising themselves. So let's see, this is the client driver. They open up a connection. They send something. Where are we starting our client thread? Are we not done the client thread yet? That's going to be the server. Okay, that's fine. So what I'm going to do is this. When we write our local host to this guy, what I'm going to do is I want to go ahead and give this guy some sort of unique identifier. Maybe right now we're separating everything by colons, right? So we're saying IP address, colon, port number. The port number gets tacked on by the server. Well, we want to tack on some way that we can uniquely identify ourselves on this side. So really, we could take, for example, maybe the socket. Just do something here real quick. See what that guy looks like. And really what's printing out here is s.toString. Okay, so that would give us a local thing, but I don't really like that. That has a whole bunch of our same duplicated stuff in it. But this is effectively our addressy looking thing from our socket. So maybe not off the socket. Let's do it off of. We do off our socket input. Let's see what this guy looks like. Basically just taking one of our Java virtual machine assigned addresses. And using that as our unique identifier, which is effectively a process ID. And that guy sucks too. What if we cast it to an object first, but we then just get a memory address? I don't think so, because this is going to still call toString on, and it'll still get resolved. It's not even worth testing. Well, let's go look and see if we can get our process ID. Wrong, but it's fine. Using old NetBeans stuff. There's a process API in Java 9. Ah, screw it. We'll just use the port number. But know that if we go and put these on different machines, that port number is no longer going to be something we can uniquely identify. And we could do it off of things like this. They will be unique, but it's, I don't know, it doesn't seem to me to be any better than a port number. All right, so after this guy gets his port number, we're gonna have to hand him a port number first. So he's going to have to be aware of what his actual personal port number is. That way he can, Jason suggested that, if a client knows about the port number he has, then he can pick himself out of the crowd of connected clients and say, okay, I'm not going to talk to IP address that's listening on the same port as the port that was assigned to me, because that's me. I'm not going to talk to that guy. So that means over on our torrent or our tracker side, after we have our port number, so actually let's just go ahead and store the port number. Int new client port number is going to equal this guy. Get next client port. Okay, so we will store that locally, but we do need to write it out to our client. So after we get our port number, we're going to say client output dot println new client port number. All right, so this is after the client has written their IP address. We have to go over to the client driver. This is where they write their IP address. We need to read in their port number. This is going to be our socket input. Dot next line. And then we'll prove we got it. So my port number is my port number. So this should prove that each guy now gets the port number that was assigned to him, and he can then operate off of that. All right, so he got on port number 3000. This next guy will get, he's port number 3001, and he gets the full list. So now he knows about his port number. Okay. Now, what we want to have the ability to do is we want to have the ability to broadcast to all of our clients whenever there's an updated person that joins, because what we didn't do in this particular case is when this guy first joined, he was given the current list of things. But when this guy joined, he received the most current list, but the original guy did not get the updated list. So we have to decide, how does a client make sure that they listen for updated lists of clients? All right, and this is going to require us to spawn off a thread on the client side to maintain a communication channel with the tracker, either a permanent communication channel or give the tracker permission to reach out to them. So we can go do this two different ways. A client could have a second thread that says, okay, I'm going to go ahead and I'm going to listen on port 9000 and that's going to mean that the tracker can reach out to me, establish a connection with me, and send me an updated list of IP addresses, then block off that connection, cut off the connection. So that would be like a push notification, if we want to think about that in like modern day type stuff, right? Alternatively, I can just leave that communication channel open that I've already established with the tracker. And that will allow the tracker, whenever he gets an updated thing, to go ahead and send it my way. But I have to have somebody on the other end to listen for that incoming pieces of information. Now, that particular thread, he's not going to do any communicating back. He's just a recipient. He receives a new dump of any new things that come in. Make some sense? So let's go ahead and do that. And I think we started writing this. So here's our client tracker listener thread. So we're going to spawn off one of these. This guy's going to go ahead and get the piece of information that we need to read in from that open connection with the tracker. So we have our tracker input, and then forever he's going to listen for an incoming list of IPs, and then he's going to update his local list of IP addresses. So client core, when we update the connected client IPs, it's probably going to delete all of them that are currently in there. Here's clear. And then we go through, and right now we're splitting them on a comma, which I guess is maybe okay, because we're going to have to further then split them on colons once we get have to deal with the port numbers to open up those connections. And this is where we're saying the client IP list was updated. So actually, is this guy already getting called? I don't think I saw in client driver us spawning that guy yet. All right, so we are getting our port number, so we're good there. We're getting our initial list of connected clients. This is when we first join. We're updating our list of connected clients, so that's where we're getting that thing where it first spits out that your thing has been updated. All right, we were proving that we got that list. We'll go ahead and leave that out there. Actually, why don't we do this? I'm going to move that into the client thread. That way we'll see whenever the tracker sends us a new updated list of IPs, proving that we're getting that broadcast each time through. All right, so our client driver, after he initially gets his list of connected clients, he now needs to maintain the connection with the tracker to get updates on connected clients. And we're going to do this by starting that thread. That's just our listener for that guy. So we'll say new client tracker listener thread. And this guy is going to take in as a parameter our input scanner from our socket. And we'll tell that guy to start. So this thread, his whole job in the world is forever to sit there and try to read in a list of IPs over that communication channel, spit them out to the screen, proving that we got an update, and then update his local list of connected clients that make up the peer-to-peer network. That's all this thread's job is. And then right now, in terms of our main thread, the client just sits there and does nothing. That's going to be the actual torrenting stuff. All right, so now we got to make sure that the server, whenever a new client connects, also goes ahead and spits that stuff out to all of the previous connected clients. So on our server side, side of our tracker thread, his way to output to the client is this guy right here, our client output. So whenever, so this is our thing, broadcast string to clients. This is the connected clients. Where's our connected clients? So let's look at what core broadcast string to clients currently does. It goes through all of our print streams and writes something out to each of those guys. When did we add that? So some tracker thread. Right, this is where we're adding that print stream, which is kind of interesting. Oh, we were broadcasting to everyone else before we added our own print stream. That's what the thing was. That way we wouldn't get that updated broadcast to us since we just got that information. So every client, the very last thing he does before he goes into his infinite loop is adds his print stream to core on the tracker. Well, the tracker adds it for a connected client. But before he does that, he broadcasts the current list of connected clients to all of our other clients. And that is through core. That's this guy here. So we'll go through all the print streams and write something out to each of those print streams. And who's the recipient of that? That is this guy right here. Person who's listening for the input stream to receive the next list of IPs. He's going to spit out that he got a new list of IPs, and then he'll update his own local list. All right, and that guy gets started by our client driver. Right here. All right, so let's see that happen. So restart our server. First client comes in, he's updated his initial IP list. There were no other clients to get broadcast to, so but this guy now has a thread that's spun up and is listening. This guy is going to come in, going to connect. He gets his updated list, but now this guy, notice, he now got that updated list. Next guy comes in. He's added himself to the list. He did read in. He's gotten his list. We're just not spitting it out here. This guy was updated with all the new connections. And the original guy, that's the thread. So this one guy updated. Only started two. Oh, yeah, I just started in the wrong place. Now this guy got the update. This guy got the update. Looks like I started it someplace else, didn't I? But wherever. I have 4 clients connected right now. He's connected. He's connected. And he's connected. Oh, whatever. Maybe I hit Control-C and then started it again. But in any case, now we're broadcasting to all of our connected clients. They always have an updated list of who's on the peer-to-peer network. Okay. Now, each client also knows now what they need to set up a server for, right? So clients are going to now have to start listening because they're establishing a peer-to-peer network with other clients. So in order to do that, they each become their own server. So we're going to need a thread for that. So inside of our client, we're going to have a, why don't we call this guy a, kind of a funny name, client server thread. Let's just say okay. So this guy would be a client server thread.java. Similarly, this guy will extend thread. Now he's going to need to know what the port number he's going to listen in on. So that needs to be handed to him when he first starts. So we're going to have a private int listening port. How do you spell listening? Is it 2 N's or 5? 1 N? Listening port. Man, that's going to be tough to spell. Copy that. All right, so I hate all of you. So yeah, in client, no, it has to match the class name. That's why I forgot him in both places. True. You should see some of Mr. Gonzalez's variable names. He has a habit of just banging on the keyboard a whole bunch of times. All right, so this guy is going to take in a int port number. We'll set this dot listening port equal to port number. Ah, there's a great reason why you should use the keyword this, so you don't misspell crazy variable name spellings. Perfect. perfect reason. All right, so this guy knows about the port number. So now we have to have our public void run. All right, and what this guy is going to do is he's going to sit here and he's going to wait for incoming connections, okay, for other people to talk to him. Now, this is where it's going to get really interesting, right? Because how many people might try to talk to him? A bunch, right? In this case, we have what, three peers that are in on the network. So he then becomes kind of like our original chat server, where he's going to sit there, accept the connection, and then do what? Spawn off a thread to go do that. So we have threads within threads within threads. So this guy will just start off by creating a server socket. Since server socket was at Java dot server socket. There we go. Oh, we probably need to do a try. So we'll create a server socket. SS, and this guy will be a new server socket, and we got to give it the port number it's going to listen on. That's this dot listening port. You don't roll the ends because it's actually Swiss. It's a Germanic language. I don't think so. Years. I think Switzerland is where the language comes from. So, but I speak, you're right, I speak Swiss and Sweden too. I've never been to Switzerland, but I've been to Sweden. All right, so there's our server socket, but that just establishes our object for it. In order to actually get an incoming connection, we need to accept an incoming connection. So what we want to do here is we probably want to do something like a while true. And let's comment this up a little bit. We're going to listen for incoming peer connections. So we'll say socket, a new peer is equal to ss.accept. All right. Oh. It'll do the import for you if you don't finish typing the word yourself. You let it finish, and then it'll import it. All right. Now we'll go ahead and catch. Okay, so we have our new peer incoming connection. So now we have established a socket connection with a peer. Well, what do we do with that? So every peer knows about all the other peers now. So every peer can now establish a connection to every other peer. So when if I'm a peer and I'm the thread that is server mode of me, right? I have incoming connections, and now I have a socket connection with one of my other peers. It doesn't matter who this is, right? This is someone who is interested in sending me bits, or he might not be overly interested in sending me bits, but he has made himself available as part of the network for being somebody who can serve bits in this torrent connection, or the swarm connection, as they call it, or I can, or they can request bits from me. Okay, so we're going to need a at least one thread that's going to handle my interest in dealing with incoming bits from this guy. And for right now, let's just spin off a single thread that gets both pieces. All right, so we're going to spin off a thread that knows about a socket for a connected peer. And that guy will deal with all communication related to that peer. Or, think about this for a second. Do we want to have a thread for every connected peer? Or do we add a connected peer to a list of open connections and then throw that in this guy's client core, and back in our client driver down here in the while true, we cycle through that list of connected clients to do our torrenting stuff. Who do we request bits from or something like that? Why don't we start with that? That way we can decide whether we actually need more threads, because you do want to consider from an OS perspective, remember the threads versus processes. What's the advantage of threads and the disadvantage of threads? Go ahead. Okay, which then also means what? Why are threads not, why do threads not automatically give us better performance? Sure, and specifically CPU time. All right, so let's assume there's 5,000 connected clients in this torrent, which is, I mean, 5,000 seeds for a torrent is not a ridiculous number. There's been seeds with more than that. So that means that your if you spawned off a thread for every swarm connection you make here, you would have in that example 5,000 new threads running on your machine. Now, can your machine handle 5,000 new threads? Probably. But now you are splitting your CPU time for this application that's already running in a virtual machine. You're splitting it 5,000 ways. Maybe not the ideal. That's kind of where multi-processes make more sense. But then you start using the whole OS's resources. So for now, why don't we just go ahead and throw our socket connection into an established connection, and we'll just keep it alive, because we're going to have a cadence between dealing with that socket. And we're probably going to have to listen at some point. One of the problems we're going to have to think about is at some point, somebody's going to be requesting bits. If we just think about that side of it for a second, if we are a server for bits to other folks, when we don't even have our file represented here yet, but if we're a server for bits to other folks, they're going to say, hey, I need bit 3. Do you have bit 3? At some point, I need to be able to retrieve that request. Some aspect of me, this multi-threaded me here, some aspect of me needs to know that somebody asked for something. Now, I can do that by having a live thread for each one of those sockets and having them constantly listening, right? Like, did you say something? Did you say something? Did you say something? Well, actually, it would just block. It would say, did you say something, and block there until you finally did say something. Or I could try to cycle through all the scanners and try to read something in from each thing with a timeout. And if nobody's there, then I just move on to the next. I try to read from them. Go ahead. Well, it's not that you would never receive it. It's it would take time for you to get to the request. Because if you had an array list of, let's say, 10 scanners for your 10 connected clients, and the guy who just sent you a message is number 8, I'm starting at the top. Like, do you have anything for me? Maybe timeout after 1 second. Do you have anything for me? Do you have anything for me? Do you have anything for me? Finally, you get this request here. You fulfill the request and move on, whatever it is. On one hand, you're probably giving up some performance there. But on the other hand, you are more quickly responding to requests. It's an interesting quandary. Is creating a thread for every single connected client potentially a lot of threads? I don't know if it's a problematic number of threads. And also you got to consider that the amount of kind of the time it's going to take us to deal with that particular thread isn't a whole lot. And one of our trade-offs we're discussing here is, oh, we're saving our CPU time, or we're splitting our CPU time between all those connected threads, right? But then we have the nature of what we're doing when we get CPU time. Reading something in from the socket is an IO action. What's special about input-output actions as it relates to the CPU? It's kind of all related to this concept of it. We're sharing our CPU time across our 10 threads in the example I just gave with Emily. So we're sharing our CPU time, 10 threads. And the thing that we're doing in communication with each of those threads is reading something in, or we could say writing something out. What happens on the CPU when we try to write something to the screen? This would go back to the time where I would have given you a sample program, probably in 200 or something. And I think we did it again in here, where I wrote a program that had a for loop that counted 1 to 1,000,000. And then I took that exact same loop and all I did is added a print statement in the middle of it. And it took a lot longer to run. Why did it take longer to run? IO is slow. Why is it slow? What's actually happening at the operating system level? But context. Oh, so you remember the word for it. So it was a trigger word. It was a trigger word. Yeah, so you'd have context switching. So the idea here would be, if we're going to be doing IO anyways, we're going to be jumping ship off the CPU anyways. So it didn't really matter that we were sharing CPU time. I think in that case, and there's probably a hybrid to this, where maybe we kind of break our clients up into clusters. Maybe we deal with maybe 5 connected clients per thread, something like that, instead of having 1 thread per connected client. There's probably some hybrid here, but we'll keep it kind of at the, let's just say the easy level. We'll have a thread for each of our clients. As soon as we read something in, we have to give up our CPU time anyways, because IO is something the operating system handles, not, well, eventually it'll come back to the CPU, but it's something that we have to jump ship on the CPU now, and then it becomes another process's problem, who gets their own CPU time, some system command of the operating system. All right, so with that in mind, we have our this new peer. We just have a socket. So now we do need to go ahead and create a communication channel with their, and man, I really think we want to have 2 threads. It's going to be a whole lot easier to think about with 2 threads. 1 thread that accepts requests for bits, and another thread that allows us to send requests for bits. It's got to be 2 threads. All right, so let's see. We're going to call this the client request thread. This guy will extend thread. And just since I'm not necessarily sure exactly what all the pieces we're going to have to deal with are here, we're going to just take the whole socket, and then we'll pull out the IO stuff that we need related to the socket, rather than pre-create the scanners or the print writer or the print streams and then send those. So we'll have a private socket. Let's call it S. All right, so there is that guy. I'm going to steal most of that. So we're going to also have a, that was a client request thread. Now we're going to have a client send thread. Yeah. All right. So the client request thread is going to, let's see, the client send thread. He's the one that's going to sit there and listen for requests coming in from each of the connected clients in the swarm. And he'll fulfill that request if he can. Just do that. And we're going to keep ours pretty simple rather than trying to, say, oh, do you have, these 20 bytes in a row or something? We're going to say 1 byte. Do you have byte 4? Do you have byte 7? Do you have byte 13? Not going to be the most efficient BitTorrent in the world, but it effectively gives us the model of how BitTorrent might work. So inside of our client send thread, we want to go ahead and we are going to need to have a request for a bit as well as the ability to send that bit back out. So we're going to have a scanner for getting our requests. And then we're going to have our data output stream for sending bytes out. Okay, similar to when we did our file IO stuff before. So it's not going to be a print stream because we're not going to be writing text. We're going to be writing bytes. Suppose we could hide them inside of text, but we'll do data. All right, so let's go ahead and create a try catch here. It's going to be needed. All right, so we're going to go ahead and give ourselves a scanner. Input is equal to a new scanner from this dot s dot get input stream. So we'll build a scanner around our sockets input stream. Right now we want to get a data output stream. There's our data output stream. Is that what we use? Data output stream? Print streams for text. This guy's going to have a request for a byte number, and we're going to then send data. We're sending a byte. I think we use data output streams. Here's our data output stream. This will be this dot s dot get output stream. That guy? There we go. What are you mad about? Oh, gotta have an equal sign there. Nailed it. All right, so let me just look up data output stream real quick. Want to make sure we didn't use some sort of wrapper for that. I think this lets us do the primitive writes where we can write a byte at a time. If it does, aha, perfect. All right. So this guy's going to take in requests and then fulfill those requests if he can. We're going to probably, we're probably going to have a back and forth. We're going to have, so the other client's going to come in and say, do you have byte 7? He'll probably just send the number 7. We'll look up and say, oh, do we have byte 7? Yes or no. We'll then have to tell him yes or no whether or not we have byte 7, so that he knows whether or not to expect to receive byte 7 from us next. So we're effectively building a protocol, because if we don't have byte 7, what are we supposed to send him? If he requests byte 7 and then immediately is waiting for the byte and we don't have it, what do we give him? Kind of talked about this before. We can try to send like a, if we were thinking about this from a normal programming perspective, we can send them like a -1 or something like that. But technically that's a byte. That might be, it's like, hey, here's the data. You asked for byte 7, I'm going to give you a -1, which I thought meant I don't have it, but now you think you just got a byte from me. Now you got a corrupt file. So we probably need to have a little protocol built in here where, do you have byte 7? Yes or no? If yes, he'll expect the next thing to come in as data. So Emily, you're right. We are going to need a print stream as well, because we're going to be writing out text as well as writing out bytes. So we'll also create a print stream. We'll call this output text. We're going to call this guy output bytes. It's got to be a new print stream built out of this .s.get output stream. Hopefully that works. I think it will. We use the same output stream for 2 different uses. I think those wrappers just treat this stuff differently, as long as I match it up on the other side to use a data input stream to read what I'm reading in an actual byte, and I use a scanner to read when I'm reading in text for my answer. All right, so first thing is we're going to wait for a request. So we're going to say string byte number is equal to input dot next line. And remember, this line blocks. So we're just going to sit there on that line until somebody actually sends us a request. All right, then check to see if we have that byte number and respond yes or no. Right, so we're going to have some way of going and checking whether we have that byte. That's going to come down to how we're going to actually store our files. So that's going to be the last piece of this. So we'll say if something like this, Boolean. So if I have the byte, I'll say output text dot println yes. Else output text dot println no. All right, and if I said yes, then I need to actually send the bytes. There's my placeholder for the actual byte, and then I'm going to use my output bytes, and I'm going to write a byte, and the byte I'm going to write is B. They asked for a byte. I somehow check if I have the byte. We don't have the infrastructure for that yet. So we haven't decided how we're storing our files. Then if I had that byte, I'll write text out saying yes, because the other side is waiting for a text answer, yes or no. And if I send yes, then I'll immediately afterwards send as data the byte. If the other guy received a yes, he would then put himself into say, oh, okay, so now I can go ahead and read the byte in from him. He was able to provide that. Otherwise, I'm just going to output no and move on with life. Go ahead. Probably. They actually might both work, but right byte's more correct. So I think right byte actually takes an int as a parameter. But this is more correct. Okay. And this is what I do forever. All right, so when we have our client send thread, this guy becomes a fulfillment thing for a client request. He'll establish his various connections he needs to speak. He'll sit there and wait to read in. This is only with a specific client, because this guy only existed. This is our client send thread. This guy only exists. Here's my client server thread. That guy only exists when a peer connects to this particular client server. So a client is both a client and a server. So what's this guy's job right here inside of my client server thread? His job is to create a server socket and forever handle an incoming connection, spawn off a send thread to deal with it. He's also going to spawn off a receive thread. I think they could call it request thread. This guy listens for incoming byte requests. This guy sends byte requests to other clients. So inside of our client send one, we can go ahead and just write something here real quick. We'll say system.out.println client send thread started. So we know that guy's been engaged. And then our client request thread, we'll write something similar in here. This is the client request thread started. And this happens whenever somebody connects to our client server to deal with sends and receives. And that server is listening on the port that was assigned to this particular guy. And who knows about that port? It's our client driver. Client driver read in his port number right here. Then he got his list of connected clients. This was my client. Okay, that's my tracker thread, so I get updates on those things. So now I need to spawn off a client server thread. So this will be a new client server thread, and I need to give him my port number. So that's my port number. I'll tell that guy to start. What did he take? Man, he taken an int. So I'll just parse the int out of my port number. So I'll start off another client server thread, passing him the integer version of my port number. I'll tell that guy to go ahead and start. That guy will come in here, client server thread. We build it with the port number. He establishes a server socket around that port number. He listens forever for other clients to connect. When a client connects, he starts off a send thread and a request thread. For homework, make BitTorrent. Go. All right, now we'll do just a little bit more onto it. I thought you were gonna play like the Freddy Krueger, you know, it's like 1, 2. Oh, that was like an alarm. Oh, I see. Okay, so make each client connect to each other client and send a request for a single random byte. You can always reply no to that request for now. We don't have bytes to send. Let me push my current version of the code. That's good. Oh. That's good. That's the socket test? No. Multi-threaded client. And remember, this is going to the torrent branch. Last 2 or 3 classes. You can go on to Slack and just see whenever I sent that message that said reminder, it's on the torrent branch. I think that was the second day I pushed to it. All right, So goal for this homework assignment is for you to utilize that string that all the clients receive and knows about all the other connected clients, split it on commas, split it on colons. So you have the IP and the port number, and then establish a connection to each of those clients and request byte 6 or whatever, right? Just request some random byte. And then they're always going to send a no, but that'll get all the threads connected and proving that they're connected. Make sense? So this is mostly a string parsing exercise, although you're obviously having to work with, you know, an increasingly complex project. Questions, comments, concerns, bribes? All right, I'll see everybody on Thursday.